Okay, we define recurrence among states of a Markov chain. Now, the next proposition is about if an only condition for a state to be recurrent. Okay, so the condition is that this series sum is infinite. So you see that the PJJ sub n is the n-step transient probability from state J to the state J itself. So, so if we consider all the possible steps n from 1 to infinity, then the sum should be infinite if only if the J is recurrent. Right. So now we take a look at the proof. We know this is the total number of visits to state J in the lifetime of the Markov chain. And so, of course, by the definition, it's just the sum of the indicator for the state to be in state J. Okay, so this is just the countable number of visits to state J. And so this is a direct formula. Okay, so now if state J is recurrent, then you will start with state J. Then the probability that we will visit the state J with for many times, this probability must be equal to 1. Okay, so and so we can see that because of that, the expectation of the total number of the visit to state J, given that the initial state J should be infinite. Okay, so okay, so now when we take the expectation for that, okay, and applying this formula here, and then exchange the series sum and the expectation because of the indicator are non-negative, so we can apply the Fubini theorem to exchange the two operations. Okay. And so we have this is summation. We have this summation. Right. So now, but this condition expectation actually with indicator actually is equal to the condition probability. And that is exactly the n-step transition probability from state J to state J. Okay, so it's PJJ sub n here. Alright, so finally, so we know that so this is true. Okay, if J is recurrent, so we prove that if J is recurrent, then this series sum must be equal. So this is the first part. Okay. Oh, by the way, I have some here. Sorry, the rest of the solutions of homeworks are visible. Because I delivered the rest of the solution of homework today, I think I have to postpone the meeting examination. So my suggested date will be next Monday. Is that okay for you? At 9 time? Next Monday. December 2nd. Yeah.
although 原本有事。
Oh, okay. So, how about Tuesday? So, okay, right? How about you? Tuesday. Okay, good. So we we make the P state. Okay. All right. So we proved the first part because the proposition says that these conditions should be an economic condition for a state J to be recurrent, right? But we just prove the forward direction. So now to prove the reverse direction, we use the counterpositive argument. So now we suppose that assume J is transient. Okay. So when J is transient, of course, that given J equal to 0, it's the initial state J, then the total number of the visit to state J should be finite, right? So, okay, for some M. Now, but we already compute that the formula that this condition probability is actually is a geometric distribution. Okay, so this is M to J. Therefore, this expectation. Okay, so this expectation will be 1 over 1 minus FJJ. Okay, and then so this should be finite number. Okay, it should finite number, and so that the sum should be finite. So prove that if J is transient, then the summation that should be finite. Because that if J transient, then the FJJ, the first return probability should be less than 1, right? We defined that before. We can go back to our definition of a recurrent state. So here, that a state is called recurrent if the first return probability times 1. So that means that if a state is called transient, if the first return probability II is less than 1. So that is the case. Okay. Alright, so now with that proposition, we can show that if J is recurrent and I and J communicate with each other, then J is also recurrent. So the corollary just says that recurrence is a class property, that in a class, in a communicating class, if one state in the class is recurrent, then all the states in the same class is recurrent. So that is the basic idea. All right, so we will assume I not equal to J. All right. Okay. Now, because I and J communicate with each other, so we can have n-state transition probability which is positive from state I to state J for some n. And also, for some n, we can reach the state I from state J, okay, in m steps. Okay. Right. So this is the definition of communication. So now we consider summation. right? We compute something summation here so this is summation of the K-state transient probability from state I to state I. Okay, and of course we can just take so this summation has less terms compared with the summation here, because that is start from n plus n plus 1. This is start from 1 to infinity, but this is from 1 plus m plus 1. Okay, so this sum is basically the index here, the steps here. Just we have some few k not included in this infinite sum. And by the Chapman-Kolmogorov equation, that this transient probability is greater than equal to 2, you can reach from I to I in n plus L plus n steps. You can do it like from I to j for n steps, from j to j for L steps, and from j to I for m steps. Okay? So we can have this low bound. And now when we sum over all the L here, okay? When sum over all the L here, because this is constant, right? We can move out. But the summation is infinite because that j is recurrent from the previous position. So this is infinite. And then, so the lower bound is infinite, right? So when the lower bound is infinite, of course, this is infinite too. Okay? So this is infinite. And so this proves that state I is also recurrent. Right. So now we prove that recurrence is a class problem. Okay. So you can say a communication class is recurrent, or a communication class is transient. Right. It's and a useful corollary here is that if J is recurrent, right? So if J is recurrent, and we know that I can be reached by J, then I and J must communicate with each other, and I is also recurrent. Very interesting. That this is because I is recurrent. So if you have a path to go, so so this is state J, this is state I. We know that we have a direct edge, right? Go from state J to state I. Okay? And because J is recurrent, so when the initial state is J, now we have some, because that J could be go up, maybe some other direction to go out from J. So it has positive probability from J to I. So if we take this step, you must be able to return back to J because J is recurrent. Okay, and so some way we have to go back. We have to go back. So that so you have so that I and J should be communicate with each other, and so I and J are in the same class, and from the previous corollary, that I is also recurrent. So intuitively, this is true, but we need a proof. Okay, so this will be taken as an exercise. Okay, so now, we have already computed all these conditional probability. Okay. So when the initial state is I, and the total number of visits to J is equal to 0, it says that you never visit state J. This probability is 1 minus Fij. Because what is Fij? Fij is the first passage probability from state I to state J. Okay? From state I to state J. So Fij is the probability that you ever visit state J when you start with I. So 1 minus this probability means that you never, this is the probability that you never visit state J. Okay? So that's here. Alright, so this is 1 minus. And the M, so start with I, alright, and then you can visit state J for M times. This M is a finite positive integer. So you will start from I, you will visit J for the first time. That is the Fij. And then from J to J to J, you have the first determined probability for M minus 1. And then you never visit again. Okay? So it's very easy to interpret this conditional probability here. And but this is the intuition, but we actually have shown this formula before. And finally, when M is infinite, it's not bad. So start with state I, and then you go right for infinite many times. And this probability is that if J is recurrent, then that this probability is just Fij, right? So this is the probability that you ever visit J, right? Because J is recurrent, so that once you visit J from I, then you will visit J for infinite many times because J is recurrent. So that we have. But if J is not recurrent, then even you reach to state J, then you will visit J for finite many times. Okay, because J is transient, so that this condition is 0. Yeah. Okay. And so you can see that it depends on whether J is recurrent or not. Then you have a distribution. So the distribution is that you can write it down. So for the case that Fjj is recurrent, right? When J is recurrent, that is this case, Fjj. So that you have infinity here. Okay, so this is M, and this is infinity, right? So you have that, and this height, right? This height is Fij. This has Fij. And for here, that this is 0. We have another pickup here. And this value is 1 minus Fij. Right? And the others, 1, 2, 3, they are all zeros. Okay? So when M is a finite positive integers, then this is 0. Because 1 minus 1 is 0. Okay? So the distribution, the conditional distribution is that the conditional distribution of N infinity given x0 equal to I, right? That's 2 it's binary. Or we usually say that what I say is that okay, so this is the distribution. So the non-variable is extended value because it can be infinite. So this is the distribution, and the sum is 1 when j is recurrent. But when j is not recurrent, when j is transient. Okay, and so when j is transient, then we have so this is n 0. Okay, and so we have one here. Okay, so 1 minus Fij, and for m equal to 1, so this is Fij minus Fjj, and then go down exponentially. So you have this way, and the probability of the distribution J, so B for Fj equal to M Fij and so this random value would be finite for real one. Okay. So you have, starting from 1, you have exponential decay. Right. So that is the, so if we take the expectation, we have this situation that if we have Ij, so in the case of if J is recurrent And if Fij is greater than 0, if this is greater than 0, alright, so then the expectation must be infinite. But if Fij is 0, Fij is 0 means that you never visit J. But you start with R. Okay? So you never visit J because the first spatial probability is 0. So even though J is recurrent, but you never able to visit J, so that the expectation should be 0. Because if Fi is 0, then with probability 1, the total number of probabilities. And in the general case, for the transient case, you can compute. This is basically the geometrical expectation. Okay. Okay. Now, once again, we know we have known this one, right? This is the total number of visits to state J. Right? And so again, we know this is the summation, right? Just shown that this expectation is just equal to this one. So of course we have the Ij here. Okay, so this is Ij here. Starting from I to J. So this is summation. This summation is infinite or 0 or equal to this one. It depends on different conditions here. Okay. So the difference is that when we consider the first position today, we are talking about the n-step transition from I to I. Okay, from I to I. So that is simple case. But here, I and J may be different. So actually, this is summation. But depends on Fjj and also in the Fij. Okay. So if J is transient. So if J is transient is here, right? If J is transient, we will use this factor later. If J is transient, the summation, okay, is finite. So the series sum is finite. When the series sum is finite, then the terms will go to 0 as n goes to 0. Right? This is the necessary condition from calculus. So if J is transient, then that you start with any state. I can be any state, right? Then you consider the n-step transition from state I to state J. As n goes to infinity, this transition probability goes to 0. Okay? So this is a necessary condition if J is transient. Okay? So we will just use this result when we consider limiting behavior of the morphology. So now we are going to study the limiting behavior of the morphology. Right. So now, remember for a state J, Fjj is the first return probability. So the first return probability actually is the summation of the return probabilities in k steps, k is exactly k. Because you can return back J in 1 step or in 2 steps or in 3 steps. Right? So they are disjoint events. And you sum over all these first return probability in k steps, for k from 1 to infinity, you have the first return probability. Right? So that is the definition. Alright, and so this is just a review, right? Our definition. So this is exiting 1, and this is the first return probability. What's the return time to stage A in K steps? All right, so that you have to visit. So given the initial stage J, then the next visit or the next return, right? Return back to J, and the time is infinite. What is this probability? It's one method. So from that, if J is recurrent, right? If J is recurrent, this probability is 0, because recurrent means that you will visit in a finite number of times. So now, in many studies, we want to know the expected transition starting from stage A, right? And return back to J. So we want to know this one, the expected transition. So we define mu Jj to be initial stage J, and we want to know that this conditional expectation of the first passage time back to J. Okay, so we call mu Jj. Okay, so this is the expected time. This is the distribution. Okay, this is the distribution, and this is the distribution. Okay, so now, it consists of two terms. One is that in finite number of steps, K steps, right? So K is finite from 1, right, to infinity. So, but whenever K is finite, so K times this one. And the other is that you should take infinity many times, and the probability is one method. Okay, so mu Jj is equal to the sum of these two terms. And it is obvious that if Fjj, okay, is less than 1, means that if J is transient, then this expectation must be infinite. Okay? Because you have a positive probability that you never visit J back. Never visit J means that you have to wait for infinite many times to return. Okay? And so but when J is recurrent, then of course this is 0. And then the expected transition needed to return back to J is this summation. Okay? But this summation may be infinite. Okay? So even though J is recurrent, it is possible that you need the infinite, the mean number of transition back to J may be infinite. Okay? It's possible. Right? So we have to differentiate these two cases.
Wait.
Yes.
Doesn't it just sum up to finite number? How can it be?
It's possible. For example, if you have a random variable x equal to say 7, and this is 1 over n squared times alpha. Alpha is a scaling factor. Right. Suppose I have a discrete random variable, and this is the distribution. And the alpha, what is alpha? Basically, alpha is the sum So it should, well, 1 over. I think that's okay. So alpha is a scaling factor, and the expectation of x summation okay. So this is the expectation. All right, and so this is alpha summation. Because this is a harmonic series. So it's possible that you have a display because that the value are all finite, right? And they have such distributions, but the expectation now becomes to infinite. So it's possible that so if J is recurrent, if J is recurrent, mu Jj is this sum, and it is possible this is infinite. So if mu J is infinite, we call this recurrent state as non-recurrent, because even though it is recurrent, but the expected number of transitions needed to return back to J is infinite. So that state is called non-recurrent, means that it's not indeed recurrent, but formal recurrent only. And but if mu Jj is finite, then we call this recurrent state as positive recurrent state. So now we have two different kind of recurrent state. One is called a non-recurrent state. The other is called positive recurrent state. Okay? Now we prove some theory that if I and J communicate with each other, means that I and J are in the same communicating class. Okay? In the same communicating class. Now, to start with, so if the initial state is I, okay, and Nij is the total number of transitions into state J up to time t. Okay, and we know that it's a delay renewal process, right? So NJT is the counting process of the so you have, so this is 10. 0, 1, 2, discrete time. So you have discrete time. We are considering multiple chain. And the state, so this is T, and here is xt. And at t equals 0, the state is I. Okay, I, right? Okay. And now And now you may so like you can, for example, you have this time apple, you visit state J. So you mark a cross here, and here, etc. Over here. So probably you visit state J, right? And then here you visit state J, you visit state J. And probably you visit some other states. So the dash means the state which is not equal to J. Alright. And so that the counting process that corresponding to a delayed renewal process. We stated that before. Okay. Okay. Remember, yeah? So especially if J is a recurrent state, right, and I state such as Fij equal 1. Okay, we already know that before. So the initial state is I. So we start with I, and this is the first passage. The first time we visit station, and this is the second time we visit station, and this is the third time we visit station, etc. Okay, so we mark that one, and then the time apple, or renewal times of a delay renewal process. Okay, so that the interrupt times, they are all IID random variables. But the first arrival time may have distribution different from the interrupt time. So that's why it's called the delayed renewal process. So we already show the renewal property, especially when J is recurrent, and when I be a state such as Fij equal 1, means that starting from IUEE, you will visit state J eventually. Okay. So that the first passage probabilities in K state becomes to a distribution because their sum is equal to 1. Because their sum is equal to 1. So this becomes a distribution, and because this is recurrent, so the first return probabilities, they becomes to a distribution because the sum equal to 1. Okay? So that's why we need these two conditions, because we require that the recurrence. So Fij Fij becomes to a distribution. It's also a distribution. So the first arrival time is this distribution. Okay? Which is equal to 1, and the interrupt time is also a distribution. Because whenever we say distribution, we have only finite value, okay? But if we consider extended value on the variables, then we allow the value to be infinite. So that is a different story. So the limiting theorem here that if I and J are in the same constraint class, and here I may be transient, maybe passive transient, passive recurrent or no recurrent, right? No matter what kind of things, well, we have this statement that given initial state I, then this is the total number of transition into state J up to time t. So it's to count the number of visits up to time t. Right? And then you divide by t. And as t goes to infinity, then with for v1, that this limit is equal to 1 over the mu jj. Okay? So it is very strong that is for v1, this non-variable tends to go to a constant, which is 1 over mu jj. So if mu jj is infinite, for example, if j is transient, then of course this is going to 0. So the first statement is a very, very strong. You can say it's a kind of law of large numbers. Okay, law of large numbers. The second term is that the partial sum of the k-step transition probability from I to j divided by n, so this is the average. And we'll go to the same limit as n goes to infinity. And so this probability is called the Ronron proportion of time that the Markov chain is in state J. Okay? So it's called the Ronron proportion of time. And if J is a periodic, then the limit here, set the limit Pij is equal to the same number, 1 over mu jj. And if J is periodic with period, then then for a multiple of these steps, the limit is equal to d divided by mu jj. So everything, a lot of things depends on 1 over mu j, go to 1 over mu j. And this result can be, so I and j can be transient or recurrent. So this is a very general theorem we can have for the linear process. Right. So I think I will give a proof on Friday, okay? Because this is a very fundamental theorem. The theorem to describe the asymptotic behavior of the Markov chain. Okay.